So, have you ever just stopped and wondered why the world isn't just a big, chaotic cloud of tiny individual atoms floating around? Today, we're going to get into the fundamental rules that build, well, everything.
I mean, really think about it for a second. What's the glue? What stops the entire universe from just dissolving into atomic dust? The answer, it turns out, is one of the most beautiful and fundamental ideas in all of science: chemical bonding.
And this quote just hits the nail on the head. The chair you're on, the phone in your hand, the very air you're breathing, you. It's all possible because atoms have this deep, incredible need to connect with each other.
Okay, so where does this need come from? Well, it all boils down to one simple, universal quest: a quest for stability. You see, nature always prefers the lowest energy state possible. Think of an isolated atom like a boulder sitting right at the peak of a steep hill. It's shaky, it's packed with potential energy, it's just unstable. By forming a bond, that boulder gets to roll all the way down into a calm, stable, low energy valley.
And the map to getting to that stable valley is something called the octet rule. You can think of it as the golden rule of chemistry. For most atoms, the ultimate prize is to have a full outer shell of 8 electrons. Getting that perfect set of 8 puts them in a state of Zen-like balance, just like the super stable noble gases.
Let's look at good old table salt to see this in action. Sodium has this one single electron in its outer shell that it is just dying to get rid of. And right next door, you've got chlorine, which is just one electron away from a perfect set of 8. So sodium gives its electron away, chlorine happily takes it, and bam, they both get their perfect octet. And because they now have opposite charges, they lock together like magnets.
Now, that whole give and take thing we just saw with salt, that's just one way to do it. It turns out atoms have 3 main strategies in their playbook for getting stable.
This chart is kind of like a personality test for bonds. First, you've got the ionic bonds, the givers and the takers, which form these strong crystalline solids like salt. Then there are the covalent bonds. These are the cooperative sharers, and they create distinct molecules like water. And finally, you have metallic bonds, with their community pool of electrons that just flow freely, which is exactly why metals are great at conducting electricity. Each strategy gives us a totally different kind of material. But forming the bond is really only the first step. The next big question is, once these atoms are connected, how do they arrange themselves in three-dimensional space? This is where molecules get their all-important shape.
The key here is a model called VSEPR theory. And I know, the name sounds super complicated, but the idea behind it is actually incredibly simple. Imagine you take a few balloons and tie them all together at their knots. What happens? They naturally push each other away to get as much space as possible, right? Well, the electron groups around an atom do the exact same thing. They repel each other and try to get as far apart as they can.
Let's start with a perfect textbook example: methane, CH4. You've got a central carbon atom, and it's bonded to 4 hydrogen atoms. So we have 4 electron balloons all tied to that central carbon. Because we have 4 identical groups all pushing away from each other with the exact same force, they settle into this beautiful, perfectly symmetrical 3D shape called a tetrahedron. Every angle between them is a perfect 109.5 degrees. It's the ideal way to arrange 4 things in space. Okay, so that's the ideal case. But what happens when one of those balloons is different? What if one of the electron groups isn't a bond holding 2 atoms together, but an unshared lone pair of electrons? So let's bring in ammonia, NH3. The nitrogen in the middle also has 4 electron groups buzzing around it, but only 3 of them are bonded to hydrogens. That 4th one, that's a lone pair. And here's the crucial difference. A bonding pair is kind of stretched out between 2 atoms, right? But a lone pair belongs only to that central atom. That means it's bigger, bulkier, and way more repulsive. It's like a big, pushy balloon that shoves all the other balloons around. So this super powerful lone pair literally shoves those 3 hydrogen bonds down and closer together, squishing the angles. Now, the key thing to remember is that we name the shape based on where the atoms are. So even though the electrons make a sort of tetrahedron, the atoms themselves form a pyramid with a triangle base. And then there's water. Water takes it to a whole other level. The oxygen atom also has 4 electron groups, but this time you have 2 bonding pairs and 2 of those big, pushy lone pairs. The repulsion is even stronger now. squeezing those two hydrogen atoms even closer together and creating that famous bent shape that we all know. So we've got these different shapes: tetrahedrons, pyramids, bent molecules. You might be thinking, okay, cool, but why does this actually matter? Well, this is where it all comes together. These tiny microscopic shapes are responsible for the properties of the entire world we see around us. This slide shows perfectly why shape is everything. Take carbon dioxide. It's a perfectly straight, linear molecule. The two oxygen atoms are pulling on the electrons, but they're pulling in perfectly opposite directions. It's like a perfectly balanced tug-of-war. Nothing moves. The whole molecule is nonpolar. But water, with its bent shape, is an unbalanced tug-of-war. The poles don't cancel out, creating an overall electrical imbalance. This makes water a polar molecule. And because water is polar, life on Earth is possible. Seriously. Its polarity is why it stays liquid over such a huge temperature range, why it can dissolve so many things, why it has surface tension, and why ice floats instead of sinking. Every single one of these amazing, life-sustaining properties is a direct result of those two lone pairs forcing the molecule into that simple bent shape. It really is mind-blowing when you think about it. All the incredible complexity of our world, of life itself, all boils down to these simple, elegant rules of attraction, repulsion, and ultimately, shape. It just begs the question, if we truly understand these rules, what amazing new materials, new medicines, and new technologies are we going to build just by designing molecules with the perfect shape?